Sir, 2 minutes. We start the today.
No problem, no problem.
So, very good morning to everyone. I welcome you again in second session of day 6 of AICTE ISTE 1 week online refresher program on artificial intelligence and cooperative Noma 5G network. In this session, Dr. Rahul Pandya from IIT Dharwad with us as an eminent speaker. I welcome you, sir. It's my pleasure to introduce sir first. Dr. Rahul Jaswant Bhai Pandya completed his MTech from Electrical Engineering Department, Indian Institute of Technology, Delhi in 2010. He completed his PhD from Bharati School of Telecommunication and Management, Indian Institute of Technology, Delhi in 2014. He worked as a senior network design engineer in the optical networking industry in Finera Private Limited, Bangalore from 2014 to 2018. Later, from 2018 to 2020, he worked as an assistant professor, EC Department, National Institute of Technology, Warangal. Currently, he is working Electrical Engineering Department at Indian Institute of Technology, Dharwad. His research areas are wireless communication, optical communication, and optical networks, computer networks, machine learning, and artificial intelligence. He is working on multiple projects such as FPARC, SERV Serve, SGNF, and RSN. I welcome you, sir. Now I would like to invite Dr. Rahul Pandya to deliver his task. Welcome you, sir.
Firstly, thank you very much, Anila Madam, for a wonderful introduction, and Garima Madam for inviting me and giving this opportunity. And congratulations for organizing this FDP, which would be beneficial for everyone. Let me share my screen and then we can get started. Is my screen visible? Let me know whenever it is visible.
Yes, sir. Now it's visible.
Okay. May I start, madam?
Yeah, sir.
Okay. Thank you very much. So in today's session, what we're going to cover is we're going to look at the basic vision or basic requirement behind sixth generation of communication. So mostly the fifth generation is about to be commercialized. So people have already started taking a leap towards sixth generation or beyond. So people are taking a look now what could be the next 10 years after this fifth generation. And so the potential, what could be the potential technologies, what are the challenges, what is the vision behind moving towards 6G? Because to me, it's pretty much delayed. If we have to start a new fresh research on 5G, it's pretty much delayed. Now, if you have to start it, it's advisable to start on sixth generation. If you've already done it, if you're working already last 5 years, then it's a disbursement phase. We can disperse the research right now and help the commercialization or other researchers. But if you're starting right now on 5G, it's kind of a bit late. So what we can do is we can think, if you're looking for a new problem or something, we can think about sixth generation. So there is a scope for next 10 years. So it would be better. So what we're going to do is we're going to look at key possibilities what are available with sixth generation wireless networks. We look at different design considerations and what could be the potential technologies that are targeted with sixth generation. And mainly, we would be targeting the terahertz communication band, so which is around 0.1 to 0.1 terahertz to 10 terahertz. So there are several challenges. Definitely, they come with the opportunities, but there are several challenges at terahertz frequencies that we will address today. We will discuss the basic architecture of sixth generation, and we will take a look how people are applying them for IoE, which is the interconnection of everything. Well, if time permits, we'll look at the cell-free cellular communication, if time permits. We'll take a look at the different technologies and the role of machine learning in sixth generation, because the earlier generations, they weren't completely integrated with machine learning and artificial intelligence. But here, the sixth generation is completely targeted to be integrated with machine learning. So we will take a look into that one also. What are the emerging trends research trends that people are targeting right now, that we will take a look, and different applications, features of sixth generation. What are the research opportunities what we have in sixth generation, that we will take a look. So why do we need sixth generation? So the key possibilities of 6G wireless communication, which is drafted by ITM 2030. So this is targeted for 2030 international mobile telecommunication. Those they're targeting those standards by 2030, targeting the peak data rate of greater than 1 Tbps, terabits per second. So if you look at the peak data rate, currently what is been targeted in 5G is around 0.02 terabits per second, and when we the 0.02 G, so see here you can see 100 times it is higher than this is my 5G, so it's 0.01, right? 0.01 terabits per second, so which is coming around 100 Gbps for 5G. This outer circle presents 5G, and this one is my sixth generation. So you can see this is coming at greater than 1 terabits per second, which is 100 times larger than fifth generation. So data rate would be definitely very high. This is an aggregated data rate. Now per user data rate, what we are targeting is around 1 Gbps, which is earlier it was around 0.1 Gbps, what is targeted right now in fifth generation, which would be delivered in next coming years. So now it is going to be around 1 Gbps per user data rate. So user will experience the data rate of around 1 Gbps. If you take a look right now, what we have is around 100 Mbps, what we see in 4G. So practically when we download it, 100 Mbps or something like the max we can see. But that is also the best case when no one is using. So the best case is we see around 200 kbps sometimes, or 500 kbps, or 1 or 2 Mbps max. Correct? So it's very less. Whereas in sixth generation, it is targeted per user data. It is around 1 Gbps, so it will be very fast. The frequencies which we are going to use, the band is 0.1 terahertz to 10 terahertz, 0.1 terahertz to 10 terahertz. And the spectrum efficiency what we are taking is targeting is 10 to 100, 5 to 10 times than 5G. So if you look at this vertical, spectrum efficiency what we are targeting is 5 to 10 times of 5G, which is targeted very high mobility and no vehicular networks with very high speed. Smart vehicular networks are in Indian scenario, it won't be that much of essential, but in other countries where the fast moving vehicular networks are into the commission, so there this kind of applications are supported, will be supported by sixth generation. Latency which is targeted is pretty much lesser in terms of very microseconds, let's say 10 to 100 microseconds, which is pretty much lesser than 5G. Connectivity density, so which is targeted is around 10 power 7 devices per kilometer square, which is very high. So
Excuse me, sir.
ultra,
Excuse me,
please
sir.
go ahead.
Still you are in first slide. Slides are not changing. Slides are not
Oh,
changing.
can you share it again? Entire screen. I was sharing entire screen. I don't know, but okay. Now let me see. Let me check. Now is it visible, sir? Sir, would you please confirm? Now is it visible?
Not it, sir. Not it.
Is okay. So nothing is visible, or let me. I have shared. I've stopped sharing. Let me know. Open and share. I'm sharing it. So it says share entire screen. I've shared entire screen now. Let me know. Is it visible, sir, now? Sir?
Sir, for me it is not. I'm not sure about others.
Okay. Should I disconnect and join again? Let me disconnect and join it again one more time so that let me try. Is it fine? I have reconnected, sir. Let me know. I'm sharing. I'm trying to share my screen again.
Yes, sir, sure.
Let me know.
Yes, sir.
Okay. So I've shared my entire screen. Is it visible now?
Yes, sir, it's visible.
Are the slides moving? Please check, madam. Are the bullet points moving?
Sir, it is showing your entire screen, your MS
Yeah, yeah.
Teams. Yes.
Are my slides visible, right, madam?
Um,
Key
Sir, no.
possibilities of sixth generation. No.
Sir, your slides are not visible. Your screen is visible. Your MS Team screen is coming.
I don't know what is
Sir, kindly
happening.
open the PPT.
Okay. Some stop sharing again, and then I'm sharing.
Okay.
Let's say window I have shared now.
Yes, sir. You can opt the option window also.
Okay. Please let me know now, madam. Are my slides visible?
Yes, sir. It's visible.
Key possibilities of 6G wireless networks. Is it visible, madam? Now?
Yes, sir. Yes, sir. It's
Now it's
visible.
fine, sir. It's fine.
Huh? Peak
It's
data
fine.
rate. Are you
Yes.
able to see that? Other bullets are moving. Are they?
Yes, sir. Yes,
Yes,
sir.
sir. It's moving.
Okay. Okay. Thank you very much, madam. We'll stretch it a bit more, 10 more minutes. Okay. I'll stay back and then we'll have whatever we have lost. Okay. So quickly I recap. The peak data rate, what is targeted is greater than 1 Tbps in 5G, which is 100 times higher than my 5G. User experience data rate, what we have is 1 Tbps, 10 times greater than 5G. And the terahertz frequency range, which we are going to target, is around 0.1 to 10 terahertz. Spectrum efficiency, 5 to 10 times of 5G, what we are targeting. Very high mobility is expected here. Latency, what we have is in the target is 10 to 100 microseconds, and it would be kind of an ultra dense user network. So there are too many users would be targeted, densified situation would be targeted, so nearly by 10 power 7 devices per kilometer. So sort of energy efficiency is very important in sixth generation, so which is targeted by 10 to 100 times than that of 5G, because energy efficiency comes into the picture because when there are because the frequencies are very high, the path losses will be very high. So what we have to deploy is too many access points. Also, the end users will be operated at terahertz also. So for them also the path losses would be very high, and they have to radiate at a higher power. So energy efficiency is very important into the picture. with very high throughput network capacity is targeted, and security is also needed very much at the elevated state. And complete AI integrated ubiquitous connectivity is expected in sixth generation. What is something missing in 5th generation? So there are two main factors which are missing in fifth generation is a complete integration of artificial intelligence, which is partially integrated with 5th generation, but not completely. So that is the first drawback of 5G. Whereas what is targeted in 6G, the AI is completely integrated. Also, the satellite communication is not completely integrated along with the terrestrial or underwater or other applications of the for 5th generation. So whereas it is the ubiquitous connectivity, which is completely integrated with the satellite communication, is also targeted in 6th generation. Correct. So there are multiple of technologies available to cater these requirements. What we have discussed, such as peak data rate, high user experience data rates, low latency, high reliability, other things are very much targeted here. So we can see here how we are going to do that. So first and foremost, we have to deploy the terahertz communication band, which is my point one. Are my slides visible, sir or madam? Just for a confirmation.
Fine, sir. Fine, sir.
Thank you. Thank you. Let me know if it goes down, okay, in between. Let me know. So I am right now in this design considerations and potential technology for 6G network. On this particular slide, I'm right now. So if you're not looking into that, so let me know. We will apply the super massive MIMO, which is nothing but the massive MIMO what we have used so far in 5G. So super massive MIMO is definitely essential. The next technology coming out is LIS or RIS, reconfigurable intelligent surfaces, or we can say large intelligent surfaces. So this kind of surfaces, they are targeted in such so that they can replace the existing relaying system which are used for amplify and forward or decode and forward applications, and these are also completely integratable with the artificial intelligence. We will take a look more into that. Then OAM, this is another multiplexing technique where we multiplex the signals using the phases, that we will take a look. Laser and VLC based communication, that is also coming, but this is something challenging. Some of the segments can be integrated over VLC or laser, but not all the segments. People are also looking at the quantum communication, but this is not something immediately will come. It may take 10 to 15 years, the quantum communication, but this is again a new one. Now there is one more interesting part coming out is, along with artificial intelligence, the integration of blockchain. That is something looking very promising, because if you look at the artificial intelligence, there are certain drawbacks, such as sharing the training data. Correct. So that is a biggest problem. Second thing is the centralized approach. That is another biggest problem. Security is the problem. When we share the data, security is the biggest problem with artificial intelligence and machine learning. Whereas if you look at the blockchain architecture, there is a shared ledger which is available with all the users, and the sharing mechanism becomes completely transparent, and it's pretty much encoded by one-way hashing algorithms using this cryptography and other things. So it's very secure. So if we integrate with machine learning, it can overcome all the drawbacks what we are facing in machine learning. So this is something, an integrated approach of machine learning and blockchain in wireless communication, which is targeted in 6th generation. We are also working on this particular topic with our research scholars. So if someone is interested in looking more into that, we can discuss. Okay, so there are multiple technologies what we have now. If you look at the spectrum, what we were using earlier in broadcast, so we were looking at the till 3 to 300 megahertz. Then in cell phone, what we have used till 5G, something like that, around, I don't know, 28 gigahertz, what we are targeting. In 4G, what we have targeted somewhere here, sub 6 gigahertz frequencies. So in 5G, what we are targeting is around this particular range, in the millimeter wave communication range. Now in 6th generation, what we are targeting is beyond 300 gigahertz to 3 terahertz. So that's the first band. Why? So people are looking at a start point at 300 gigahertz. So that is 0.3 terahertz. Why? Because these CMOS chipsets are available, and the antenna front ends are primary version of antenna front ends are available at this particular frequency. Still, it is pretty much higher than 5G, which is around 28 gigahertz. So still, it is pretty much higher than, and it can be extended till 3 gigahertz, 3 terahertz, and after that, we can target it till 10 terahertz of bandwidth. Correct. Now the question comes: will it harm human cells? Right. So we were thinking that it may harm human cells in 2G. We were thinking in 3G also. We were thinking in 4G also. It will harm human cell. We should not use it. Now we may think in 5G also. The people are already thinking about that. But it's pretty much straight and simple. Using this spectrum, we can see it will start harming when we go for the X-ray imaging or gamma rays imaging, which we use in cancer treatment. Correct. If we go for the petahertz like 10 power 15, or we go for exahertz like 10 power 18, definitely it will harm the human bodies and other damage the cells, but not at this terahertz or below that. So it doesn't make sense to to get in that discussion that it will harm the human discussion, because people are going to use it anyway when they see the advantages. So this band which we are targeting, terahertz, 0.1 to 10 terahertz, which is a targeted band in terms of wavelength, you want to see it becomes 0.03 to 3 mm range. Now, so you can see we are going very high in frequencies and very low in wavelengths, because when we go high in frequencies, they go very low in wavelengths. So the path losses, they become very high when we go at very high frequencies. Correct? So that's a major challenge, but it comes with very high data rates. We can support very high data rates. Now there are other challenges also. We will take a look one by one. Correct. So if we first, which is targeted, is the lower terahertz band. Why? Because the CMOS chipsets are available right now. The primary version of CMOS chipsets are 275 gigahertz, around that frequencies, around those frequencies. The initial front ends are available for 6th generation. They are very expensive, but they are available. Correct. So what are the key possibilities? We get the higher terahertz frequencies. We get very high data rates. We get very high data rates in terms of 1 terabits per second, which is very fast. But it comes at a cost. The path losses are very high at higher frequencies. So the range of transmission, is very limited. Are my slides visible, sir? Would you please confirm?
Yes, sir. Changing, sir. Fine, sir.
Okay. So range of communication is very limited when we deal at the higher frequencies such as terahertz. The major drawback is we have to deploy too many access points, smaller access points, to establish the coverage. That is the major bottleneck. That will straight away add in the bottom line and increase the cost. On the contrary, we can support very high data rates, so that can be compensated with that argument that at terahertz frequency, though we have to have deployed many access points to support that kind of communication because of the high path losses, we are going to get in terms of tremendously high data rates. So that is the advantage. So definitely the distances which are going to be supported for transmission in at this point 1 to 10 terahertz, which would be very lower than 4G and 5G, which would be very lower than 4G and 5G. But the data rates and spectrum efficiency would be very high compared to this. Now, when we go at this kind of higher frequencies, if you look at the wavelength range, which is very low, correct? Because frequencies are high, wavelengths would become very low. Even if we come into the picture, into the beam, let's say that pencil beam for 6th generation is transmitted, and even if a person walks away, there would be a human shadowing impact. Even if we have to penetrate through the wall or any kind of like glasses or any artificial walls such as wooden wall or something, the losses are very high. So the coverage becomes very difficult. Now that can be compensated with highly directional pencil beams through beam forming. So those antennas must be equipped with very multiple reflective elements which can direct my beam in a specific direction and give me the higher gain. because if we radiate across multiple directions, we will not get the higher gain. If we radiate into a specific direction, we will get the higher data rate to overcome this higher path losses of sixth generation. Higher spectrum efficiency we will achieve definitely through supermassive MIMO. So that is another advantage of sixth generation. Correct. So now there are some problems at sixth generation. These are very, when we talk about 6G, it looks very fancy, but there are multiple problems that we have to deal with. First one is the atmospheric absorption. Atmospheric absorption. So if you look at this, this is my around 28 gigahertz. Correct. 28 gigahertz. So atmospheric absorption is very low. This is my 5G around around 0.1 dB, which is very low. 0.1 dB per kilometer, which is very low. Even if you look at 4G, which is sub 6G around, it's very low, nearby 0.002 or 0.003 dB per kilometer. But when we go above 100 gigahertz, the atmospheric absorption becomes very high at higher frequency. This is a free space path loss and atmospheric absorption. So you can see at 300 terahertz, the atmospheric absorption is nearby 1 to 2 dB per kilometer, which is pretty much high. Right? Second, the lower frequencies, right, they are not that much prone to the scattering impact. But when we have the wavelength, which is, you can see 0.03 nanometer or 3 nanometer, which is the size of a dust or maybe, snow or that sort of thing. So my scattering or me scattering becomes very severe at this higher frequencies. So that is another challenge. Correct? At this higher frequencies, that is another challenge. Now we use this particular band because absorption is pretty much flat here. So what people are targeting is around 200 to 300 gigahertz at the initial setup for 6G. Definitely we are going to have 1 dB per kilometer, but what people think that, okay, we will have highly directional antennas, we will penetrate pencil beams in a specific direction, and we will quickly adapt the directions of those beams with high mobility so that we can overcome those high absorptions. So that's people are targeting right now. Second major challenge is a rain attenuation. Rain attenuation. When we move to the higher frequencies, correct, the rain attenuation would becomes higher. But one good news is beyond 100 gigahertz, it doesn't increase that much. So it will not cause beyond 100 gigahertz. It will not cause any additional impact. So let's say around you get around 10 dB per kilometer under the healthy range situation. Let's say 25 mm per hour. Correct? Let's say 25 mm per hour under the healthy rain situation, normal rain, moderate rain situation, not too much of rain, raining or not too much too less. 25 mm per hour. So which will give me around 1 terahertz. At 1 terahertz frequency, I'll face around 10 dB per kilometer of the attenuation. Okay? Which is 4 dB. So if you look at the 28 gigahertz, if you look at the 28 gigahertz, which is around 4 dB per kilometer, which is around 4 dB per kilometer, 28 gigahertz, which is around 4 dB per kilometer. So pretty much higher. Rain attenuation is one more trouble. Correct? How are we going to do that? Additional antenna gain, which will have more number of array antenna elements with adaptive beam steering. So we can radiate more power in a specific direction and overcome this. Correct? So we have to transmit the higher power. There is no escape from this one. Transmitting the higher power, there is no escape. We have to do that to overcome this attenuation. Third major challenge is the scattering. If you look at the microwaves, is my everything is fine, right, sir? Slides and everything is visible, right? My voice, everything.
Yes, sir.
Okay, okay. I'm just checking because there was a problem in connection and
Yes, sir.
so, okay, okay. Thank you. So if you look at the
Prashant,
microwave domain, when we hit any surface, let's say wall or any surface, microwave frequencies, they were pretty much lesser. We have seen the spectrum. So it remains pretty much smoother for them. So there is not much specular scattering in microwave domain. So what we have right now in 4G, right, sub 6G frequencies, we do not face that much of scattering. That's why there is no trouble with this. But when we move to the terahertz frequencies, let's say visible range or IR, let's say, or terahertz range, correct? We face the scattering, diffuse scattering. So when we hit any wave, it's going to scatter in multiple directions. So let's say if it is reflected nicely or penetrated nicely, so what we get it a higher beam, higher powered beam, which gives us higher SNR or SINR if you take interferences also. But when there is a scattering, we are going to lose our power in the scattered waves, and we lose our SINR or SNR. So we'll not be able to cover up our signal at the receiver side. So this is another biggest challenge what we have, correct? So this specular scattering is very strong. Diffuse scattering, and this is very serious issue in this particular domain. So generally, how people measure it with a practical domain. So you hit a beam at a terahertz, what a particular reflecting element or anywhere, and you have to just put a put a receiver at a particular angle. So this is my, let's say, incident angle. This is my reflected angle, reflected waves angle. You put a receiver side, you get the max power here. Now what I expect is very lower power at the other angles, which is appearing in 6G, but sorry, which is appearing in 4G and 5G. But at 6th generation, at terahertz, when you hit the beam and reflect it, there is a scattered wave. So which is going to, so I'm going to lose my power in this specific, all the scattered waves. So I'm going to lose my BER here. So that's a major challenge. That is the open challenge above 100 gigahertz. That's an open challenge above 100 gigahertz. Okay. So one more challenge. This is one more challenge. Partition losses. When you have indoor materials such as drywall, glass wall, or maybe steel doors, or office whiteboards, or any other. So if you look at the frequency ranges, when I have 28 gigahertz, which is my 5th generation, and I have a drywall, let's say thickness is around 38 centimeter, which is pretty much high thickness, right? So very good thickness. I face only around 6.8 or 7 dB of attenuation. Whereas if I move to, let's say, 140 gigahertz, very high in frequency, right? So 0.1 terahertz if we think. So it is around 0.141 terahertz, 0.14 terahertz. So which is 140 gigahertz. Even if the thickness is pretty much lower, let's say it's here 38 centimeter, even if the thickness is, let's say, 14 centimeter, 15 centimeter, my attenuation at higher frequency is 15 dB. So we can see thickness is almost one half, or more, even less than one half, but the attenuation is pretty much double or more than double. So which is a serious issue in 6th generation or terahertz frequency. We're going to face very high losses in partition reels. If you take a glass as an example, so you can say 0.1 to 10 terahertz, 0.1 to 10 terahertz, 0.1 to 10 terahertz, just the minor thickness of a glass, let's say 0.5 centimeter. I'm going to face 15 to, so I'm going to face 15 dB if you have a centimeter of 0.16 thickness, and I'm going to face a 26 dB of attenuation loss if you have a thickness of glass wall around 0.5 centimeter. So we can see when we have to provide the coverage in a building, we are going to face this kind of higher losses. So this is very serious. This is a serious issue. If we have a solid wood, we are going to face around 14 to 26 dB at terahertz frequency range of attenuation. 14 to 26 dB of attenuation for different thicknesses. Definitely, when you increase the thickness, attenuation becomes high. And when we increase the frequencies, again attenuation becomes high. So this is another challenging and serious issue, right? So there are other materials we have, correct? So now when there is another challenge is like free space path loss. Free space path loss. This is another bigger challenge. In this figure, we can see the path loss when we increase the transceiver distance, the separation between transceiver. That means, let's say, source and destination. Let's say source and destination. When we increase the separation between these two, my path losses are getting increased. Now that increase is pretty much serious when we have 140 gigahertz and beyond. So let's say 5G, this is green line shows my 5G. This green line shows my 5G right now. This green line shows my 5G right now. This green line shows my 5G right now. And this red points shows my 0.1 terahertz and beyond, so it's above 60. So when I go higher in the frequencies, my path losses are getting high. Also, when the separation is increased, I'm going to lose my this distances, and I'm going to lose. Yeah, is there a, am I reachable? Correct, everyone? So my received power is kind of reducing when I increase my distance. Now this is happening because of the path loss formula. The free space path loss, free space path loss. Here you can see this is my frequency component. When I increase my frequencies, let's say 4G to 5G or 5G to 6G or even beyond, this component, free space path loss component, is going very high. This is becoming a very serious challenge. Apart from that, we will have the atmospheric absorption. Apart from that, we have the building penetration losses. We have the human shadowing. All these components will add to a combined high path loss. All these components will add to a combined high path loss. Okay, combined high path loss. All these components will add combined to very high path loss, and I'm going to lose my signal strength. This is the biggest challenge in 5G. So I'm not able to, I will not be able to transmit, let's say for 5 kilometers, 10 kilometers, like in that particular range. I'll be able to transmit, let's say, less than 1 kilometer, correct? Less than 2 kilometers. So my access points, they have to be very closely located to provide that kind of coverage. One more thing is human shadowing impact or human blockages, because we see when you penetrate at the terahertz frequency, if there is no blockage, we see around no very lesser loss. And when there is a blockage, even we passed by between the 6G wave, we will see the dip of around 6 to 7 or 8 dB of dip in the signal SNR. So we lose the signal by 6 or 7 dB even if a person is passing by through that wave. So this is kind of a very huge loss, correct? Outdoor to indoor penetration is another biggest challenge what we have seen in those materials, correct? Now if someone wants to model that, what we have model is with our scholars is we have learned from this new sim. They have the open source 5G and 6G channel model simulator software available at this. So we have learned from that and we have developed our own code enabling all this component of the path losses and tried to study how 6G behaves. So if someone is looking to download this particular tool, you can download and modify as per your research work, correct? So quickly, if I summarize, the channel modeling and channel capacity that will be impacted at terahertz by absorption and drain attenuation, path losses, partition and penetration losses, human blockages, correct? The channel capacity at terahertz needs a novel path loss model, and the power allocation and new radio access technologies, because we have all these challenges. So we have to allocate the power very nicely to all the channels, and we need the beamforming antennas to overcome the short propagation distance and high losses. Definitely we will get all this with in in the terabits per second range. We will get very high data rates, but that will come with high path losses and high number of access points. So, and one more thing is the scattering impact is very much difficult for terahertz frequencies, correct? Now what we have is this domain commercially we have around the front ends available above 100 gigahertz to 300 gigahertz. Different vendors will code the different frequencies, but they are very expensive. That is the biggest challenge if you have to procure a lab setup. That is very expensive. In terahertz communication, what we need is no very good CMOS chipsets and hardware materials which can operate at terahertz frequencies at a higher speed at that kind of higher frequencies. So, and which we need a robust beamforming mechanism, correct? So which will overcome all these absorption losses, scattering, higher path losses, human blockages, higher attenuations, and all this what we have discussed so far. We need low complexity based low power hardware circuits which can be addressing all these issues what we have discussed. We need to have a channel and noise modeling. So with we also have to have with low energy efficient modulations schemes and low density channel codes when we design the hardware. These are the open challenges what we have. We have to design ultra massive MIMO or super MIMO, which is suitable for sixth generation. And all this is another one is the synchronization is the trouble. So the hardware must be synchronized nicely, correct? So that was the first phase of sixth generation. Now we will quickly take a look at the architecture of sixth generation. How are we targeting? Before I get into that, if there are any questions from participants or any, if I'm not reachable, sir or madam, Tingra madam, Anila madam,
Yes, sir.
am I reachable? Slides, everything is visible.
Yes, sir. Everything is visible and
Okay.
you are
If there are
audible too.
questions in the chat box, please let me know or anything. Okay.
Yeah, sir,
So
sure.
what we are targeting in the architecture is we want to integrate all three segments. I mean, all the segments we want to integrate technically. So we want to integrate air segments, we want to integrate space segment, we want to integrate underwater segment, right? All three segments we're trying to put a ubiquitous coverage across all the segments with an integrated architecture. So we want to go with the satellite integration with the air segments and terrestrial and underwater segments. This is how it looks like. Perhaps a ubiquitous or integrated architecture for sixth generation, where you can see my aerial segments, what I use right now through mobile, right? So base station, and so they are integrated with satellite communication. They are see, it's difficult to provide the coverage over the sea. So mainly it would be integrated through the satellites for the underwater, water, and over water communication. So when we cannot deploy the, definitely the movable access points can be deployed, but the oceans are very big, it's not feasible to do. We can do on demand, but no, mainly it would be integrated with the satellites. Now indoor applications, there are different technology segments available for IoT. So indoors are very much going with VLC, visible light communication. They are working very nicely for indoor, okay, but it's not suitable for outdoor and long range. So for indoor, these segments can run over VLC. FSOs can run over the buildings, very nice. So FSO backholes, correct? Free space optics based backhaul. So when we have very big buildings, or at the roof, we can deploy the laser sources and we can establish the connections, correct? And outdoor communication, when we are expecting high mobility, then we have to go with the RF communication at terahertz. So terahertz, no, what we frequencies what we are looking at with RF antennas and others. So all these different segments of frequency technologies have to be integrated, and it's very difficult to operate this kind of integrated network. So artificial intelligence is mandatory. Everything would be driven by AI. All the segments would be driven by AI. So something is coming up, like again, this cannot be integrated centrally through AI. So again, the distributed learning or transferred learning along with the blockchain can play a crucial role in achieving this kind of difficult architecture. So you can see people are applying different sort of learnings like supervised, unsupervised, semi-supervised reinforcement learning to allocate the resources, to build the different protocols, to operate the network at efficiency, optimal level. All these things are nicely working out here, correct? So these people are trying to establish a ubiquitous connectivity and accepting that challenge and operating them using AI. Or a different version of AI could be there. It's like deep learning along with neural networks like CNN, or different neural networks algorithm can be applied. So potential technologies at terahertz, if I look at this, how can I achieve it? I have to integrate with AI and big data. That's what I have to, because the network complexity is higher, so data would become very big. In so we need a big data analytics and AI's collaboration in this particular thing. We need a different radio access technology because the connectivity is massive. So we have to go with a different radio access technology. So earlier days we have used OFDM. People talked about NOMA. Now people are talking about hybrid NOMA OFDM version, which can integrate advantages of both the schemes. So people are targeting 6G. This is not something fixed, but people are proposing this for 6G. There could be different radio access technologies also. So it's an open field for for working. SM MIMO, supermassive MIMO, is another research field for sixth generation. People are looking at VLC based 6G or laser communication or FSO based 6G also. This is another research domain for 6G, what people are looking at. People are also looking at quantum communication and computing sort of thing, but I don't see anything coming in the immediate future, but this will take some time because the qubits, they will replace the hardwares also, so we have to deploy the different hardware structure. So OAM is another one. This is also an interesting orbital angular momentum based multiplexing. OAM, we will take a look how we do that. People are looking at resource allocation in such so that they can achieve energy efficiency, spectrum efficiency, correct, beam forming. This is another interesting one, large intelligent surfaces or reconfigurable intelligent surfaces. These are very much my interest right now, so we will take a look, correct, how people are looking at the dynamic slicing, molecular communication. These all are ongoing fields. UAVs are also very much, but I don't see that much of application of UAV because this will remain fantasy for next 10 years. So, correct, supplying. So this can help, but there are no business cases. See, some of the research works, there are not many business cases. So they will stay on the papers itself. So it won't scale in terms of businesses or something in the revenue based model. But anyway, for a research, this can be another one good thing also, that remote locations can be driven through unmanned aerial vehicles. Rather than providing UAV, I can integrate with satellite and put it on a terahertz nearby that location. So that can be possible. Okay, so these are different things. There are several applications like AR, VR applications or ubiquitous applications, IoE, or different healthcare applications. This you can explore. What we want to say is now that friends, what people are working on right now. People are working on 6 major trends. So first, they are trying to expand the coverage because the path losses are very high, and they want to expand the coverage by integrating multiple of those segments. So this is the immediate requirement. Increasing the system capacity is another one, correct. They want to integrate the core architecture, the 3D architecture, with AI capability. They want to, people are looking at inventing some sort of new resource modulation schemes where you can have infinite bandwidth theoretically, but not practically, but theoretically infinite. So OM can give us very good bandwidth, but again that goes in the optical domain. So this is again limited for certain applications, so that we will take a look. And resource allocation utilization methods, definitely it's a traditional problem, so that people are looking at. They're looking at the terahertz visible band, how the cognitive radio will work, this and that. People are also looking expanding the coverage. The best idea is to integrate with the satellite communication with the terahertz band, with the terahertz and with the terrestrial communication. So this is something, but the problem comes here is the satellite communication is highly impacted by delay, higher delay. So that is one more bottleneck when we integrate with satellite communication, correct. The transmission delays are very high. That's the major bottleneck. So terahertz and visible light communication, we have to overcome. Why we are going in terahertz and visible light? Because the current spectrum is licensed, and it's almost everything is occupied. So 4G spectrum, like sub 6G, correct. So that's why we are going for 5G. So sooner or later it will be occupied. So people are looking at the terahertz. It's a very wide band and unlicensed. It's unregulated, zero point 0.1 terahertz to 10 terahertz. It's a very wide band spectrum. If you look at the visible light spectrum, it's 400 terahertz to 800 terahertz. It's very wide spectrum, correct. So we have a very, the spectrum scarcity is not there, so we can go with that. So this is my terahertz spectrum, 0.1 terahertz to 10 terahertz, and this is my visible light spectrum, 400 terahertz to 800 terahertz. So really, we have very wider spectrum here. So the things comes with higher path losses, which we have to overcome, through the beam forming. So the front ends, correct, how we are going to get at the terahertz. So the traditional method what we have is the frequency mixing based mechanism. So we put the frequency mixers to draw the signal from lower frequencies to higher frequencies by mixing up at the intermediate frequencies and bring it to the terahertz. Second one is a direct modulation at the terahertz communication system. Modulate the baseband signals directly into the terahertz carrier on the directly on the terahertz carrier wave. Correct. So this kind of technologies people are trying to build upon. What are the opportunities and challenges? The hardwares are very expensive. Hardware components are not available. Firstly, available, then they are very expensive, and they are not available at, let's say, above no above 300 gigahertz. So it's available at, let's say, 0.1 terahertz to 3.3 terahertz. So it's around 300 gigahertz. Okay? So they are very challenging. They go into CR, like 2 CR, 3 CR. This kind of costs they're quoting right now. So it's very challenging to build up the lab setup unless we have a generous funding, infinite funding, what I say technically, which is not available. So what people think that, okay, we can work on theoretical estimation for the channels, and we can study that what happens, and when hardware goes cheaper, we'll do the measurements. Correct. So networking is also another challenge and opportunity. Bandwidth enhancements is another challenge and opportunity. People are looking at MIMO with VLC. That is also intelligent dynamic spectrum accesses. These are also the research opportunities what we have. People are also looking at cognitive radio with intelligent spectrum sharing. Correct. So where we share the spectrum in such so that with the sensing mechanism, where with the intelligent management, so that the SNRs or SINRs can be improved. A symbiotic radio, something which is coming into the 6G. Symbiotic radio, something which is coming into the 6G, where you have heterogeneous networks that they cooperate with each other and share the resources. Heterogeneous nets, they cooperate with each other and share the resources in such so that the performance remain intact, and co-living can be possible, right? So it can enhance the performance and cooperation can be possible. So these are other research opportunities. One more thing is, the biggest one is, if you look at the beam forming, that is very important in sixth generation. As we discussed, the path losses are very high. As we discussed, the path losses are very high. So we have to, the path losses are, since the path losses are very high, we have to deal with those high path losses through the beam forming, adaptive beam forming. So we have to have the pencil beams, which are highly directed, in a specific direction to overcome those path losses. So if you use the meta surface lens based antenna, we can see the hardware complexity is very high. Apart from that, if we use a metamaterial based antennas, they are highly directive, and they're very compact and lesser bulkier. So there you can see the those antennas are very, very much compact, and they have very good reflectivity in a particular direction. So we can adapt our beam very quickly, and they're programmable. They can be integrated with artificial intelligence. So we can quickly trace our beam to improve the tracking accuracy. This is sort of a densification of my cells, so where I can target ultra user dense network. So but the problems are like network architecture, mobility management, interference management, resource allocation, and security. These are the challenges in this particular field. Correct. So what was the past? The past was, we have a mobile communication system, satellite communication system. They were independent. It's kind of a 2D network. So now what we are targeted is integrated terrestrial and satellite communication, and with other segments also, like underwater, overwater, indoor, outdoor. All this are integrated in 6G, and 3D code structure is needed. For that, artificial intelligence is in the key part. Now, one more step, security is coming into the picture, decentralization is coming into the picture. Correct. So because of the blockchain over the AI, the integrated approach of blockchain and AI can play a crucial role. So what we are looking with our research scholar right now, we are working on this one. We are trying to build the architecture and protocols, which are AI integrated blockchain protocols for 6th generation wireless network. So that's what we are working right now. If someone is interested in collaborations, they can come up. One more research field, what people are looking right now is the information, the energy transform over the information waves. Correct. So when we have wireless waves, I mean the waves what we are transmitting over that, why can it not carry the energy which can be used to charge the batteries along with transferring the information? Why can we not carry the energy over the waves what we are using to transfer the information, which can be used to charge the batteries. So this is sort of energy harvesting, which is a traditional field. So people have already started looking into this possibility. So if someone is interested in one more research field, which we are also working with our other scholars, research scholars here at IIT Dharwad, is looking at the role of reconfigurable intelligent surfaces or large intelligent surfaces, which can be a perfect replacement of traditional relaying system, which can be a perfect replacement of a traditional relaying system. So in LIS or RIS, it has the capability to alter the properties of the electromagnetic waves. It has the capability to alter the properties of the incident electromagnetic wave. So for an example, I am hitting my signal on RIS. It can improve my amplitude and then put it back on the network again towards the destination. Now, the advantage this one is a perfect replacement for the traditional relaying system such as amplified and forward or decode and forward, because they are semi-passive. They can be fixed on a wall. They can be pastable. They are pastable on the building walls. They are semi-passive also. So they are very low in power consumption. And they are highly programmable. So they can be integrated with artificial intelligence. So they can act as repeaters or intermediate relays at a low power cost. So they are very energy efficient and they are programmable so that we can change the attributes of my electromagnetic waves or incident waves in such by dealing the different properties what I have to achieve. Correct? Supermassive MIMO. People are targeting with 10,000 array elements of the antenna, correct, and trying to achieve very high spectrum efficiency, improving the SNR also as per our basic Shannon's and Hartley's formula what we have. The problem is no different RF and non-RF integration is very important because we have the VLC, we have optical segments on FSO, we have satellite links, we have terahertz links. So all this they have to be integrated. There would be converters in between from one technology domain to another technology domain, right? For an example, backhaul is supported over the optical fiber cables, but there is no escape to it. Front hole is supported at, let's say, terahertz or let's say at gigahertz, what we see generally for in the mobile communication. So we need an integration in between from optical to RF and RF to optical domain. Similarly, VLC also, we need to do the optical to RF and those sort of things. Am I audible? Just an intermediate check. Is my slides, is everything fine? Any questions so far? Is everything going well?
Yes, sir.
Okay, okay. Thank you, madam. Just an intermediate check because, okay, thank you. So, so the problem is, okay, so then the problem is the integration part. So different segments have to be integrated. So this is another research domain what people are looking at 6G. So please note in 6G, nothing has been started at a great level right now. So everything is right now at a planning level, like a discussion level or review level, that kind of thing. So the ground is completely open if someone is looking to start your research. Ground is completely open. You put a foot and everything is yours. So all the fields are open. There are not many applications or not many papers available. So this is an opportunity for us. Correct. So second one is second is people are looking to build new modulation formats for multiplexing, like OAM based multiplexing. Correct. So far what we have used is the traditional plane for multiplexing. When we use the now what we use is we are proposing orbital angular momentum based multiplexing. Orbital angular momentum based multiplexing. Okay. So in that what happens is there are different orbital angular momentum based waves which are differing in the angles, and they can be multiplexed over different degrees. If that can be muted, someone's no, some isolation is needed. Okay, there is some background noise coming. If a mic is on, please mute. Okay, so OM modes, let's say this is first signal, this is second signal, this is a third signal, correct? So you can say OM modes, orbital angular momentum modes. This is my signal. So our baseband signal can be modulated over this optical signals, which can be multiplexed at different degrees, and they are transmitted. Now, advantage is technically we have the infinite bandwidth because the phase is, on optical signals we have multiple degrees. Even see, please note that the wavelength could be one only. On different degrees we are trying to multiplex. So at different wavelengths, again there would be OM multiplexing. So technically we have infinite bandwidth, correct? Which is not possible definitely practically, but still we have very large bandwidth, and those signals are called OAM modes, orbital angular momentum modes, correct? So which is a new way to enhance the capacity in 6G. But now the bottleneck comes. This is going to be over the lasers. You need a line of sight communication. If there is a divergence, or maybe if there is a misalignment, we lose the signal straight, we lose the connectivity. So this is on an optical domain. So this is highly suitable when you have, let's say, high rise buildings, and you can align both of those in front of each other and then trace it. Okay, that is possible. But when we have a highly movable segments, let's say vehicular segments, this is not possible. We cannot apply this technology there, right? So this is a disadvantage of that. So when we have static connectivity, let's say two big buildings, you want to maintain the connectivity, we can deploy these OEM sources at the roof of the building and then establish the connectivity. This will work very nicely, but not in highly mobile situations. So that is one. So here you can quickly see, let's say this orange is my mode number 1, green is my mode number 2, blue is my mode number 3. So okay, so multiple modes, they are multiplexed together, OM1, 2 and 3, they are multiplexed together and they are transmitted, correct? At the receiver side, you can see this is how it looks like. This is my mode 1. If you look at the top view of a multiplexed wave, this is my mode 1, signal 1, this is mode 2, signal 2, this is mode 3, signal 3, right? These are transmitted, and at the receiver side all modes are demultiplexed and delivered to the this one. So disadvantage is line of sight. That's a major disadvantage, but it comes at a very high capacity, correct? As I said, it can be placed on FSO, free space optics, correct? It can be applicable in this particular scenario only. Now the next segment is VLC segment. What people are looking at, that the LED bulbs, they are very good. They are using 400 terahertz to 800 terahertz, but which is the advantage is it can support very high data rate for a low range within the building, or maybe where there is not much sunlight outside, right? So because that daylight noise is limiting this one outside of the building. So within the building it works very nicely, visible light communication, but not at the outside of the building. So this is another segment, but it comes with a challenge, correct? So we have to look at that, which segment it is and where are we dealing. So based on that we can deal in that way. For an example, let's say Wi-Fi access points, we can set up over the campus, college and somewhere like that, right? We can put them over the street lights, or we can put them in the building. But when we have, let's say, no, open field, the Wi-Fi access points cannot be possible. We have to go with the large scale base stations only and radiate the higher power. So now one more research field is the quantum communication. Quantum communication, what we used so far is traditional bits like 0 and 1. Separately we are transmitting like classical bits. Whereas in quantum communication, what people are targeting is information has to be encoded in quantum states by a superimposition of both the bits, so which are called qubits. So instead of transmitting 0 and 1 together, we take or generate the photon or quantum state in such so that it would be the superimposition of both the bits. So technically we transmit only half the bandwidth here than what we occupy here in the classical bits. Now the advantage is this this quantum states are highly secured, and they will improve the data rates because it's very half. Even at the source it's half. Nothing is transmitted before, even if the source, because the moment when we do the superimposition, correct? So uh, because of this the bandwidth becomes only half. So instead of transmitting 0 and 1, I do the entanglement, and then I transmit only the superimposed position, the quantum state. So for an example, this is my quantum state. only one quantum state I transmit. So half the bandwidth I even required to transmit anything, even if I apply other technologies to save the bandwidth. Okay, so that's one good. But the only thing is we need the hardware for that. So that comes, uh, you need quantum computers, quantum mobiles, quantum, everything should be on quantum, because that's a biggest hardware shift, which will take 10 to 20 years, but that will come after down the line 10 to 20 years. So and the quantum key distribution, quantum teleportation, quantum repeaters, people are working on this kind of things. Quantum repeaters are very good to extend the reach of my communication. These are the challenges and technologies what we have seen. Now we will see what is the role of my machine learning in sixth generation, right? So machine learning is mandatory. There is no escape from that. Human intervention is not possible in this, because the network dimension would be very complex, and without machine learning at this scale we will not be able to operate. So machine learning is mandatory. Even people are looking at a blockchain along with machine learning to go to the next level, correct? So what we apply is the basics. I'll quickly brush up. I know that we know already, so quickly brush up. uh, People use supervised, unsupervised reinforcement learning, correct? There are several algorithms. Supervised algorithm is mainly used for classification and regression, for estimation, correct? Unsupervised is used for prediction, such as clustering algorithms what we have, and reinforcement based algorithms are used for decision making. So it's kind of a trial and error method. Learn, make a decision, learn, make a decision, like that, correct? So these kind of things are applicable. So now the biggest challenge, what I want to press is, data is not available for training. If you start any work with AI in 5G or 6G, the biggest challenge is where we get the training data sets, high quality training data sets, correct? That is very difficult. We don't get sometimes. So we haven't found any training data sets. So we decided, let's see what are the baseline assumptions what we have in channel model or in other models. Based on that, let's generate our own data sets and make it public, make it open for change, for a change, so people can add and contribute to improve those data sets. So that's what we think. That's what we think right now, and then we'll make those data sets public what we have generated at our own. So that's the biggest challenge. Deep learning we use for classification and regression. However, the performance of deep learning is highly related to the tricks which we apply in modeling when training those models. So now this is something very catchy. Reinforcement learning people are using a lot, such as Q learning or deep Q networks uh, for the resource allocation. So this kind of things are very nicely applied by researchers. For example, Q learning. But the biggest disadvantage of the Q learning is like it records all the actions and the outcome. So and the training experience. So what happens then when we have too many transactions, it's difficult to trace that kind of bulky array of all the records. That is a major challenge, correct? So and people are trying to hybridize both the deep learning and reinforcement learning, because there are certain disadvantages of deep learning, certain disadvantages of reinforcement learning. So people say, okay, we hybridize both of those, overcome the disadvantages for each. So this is what also people are looking at. Now this is something new, because since we said the network becomes very big and bulky, and we want to integrate all these segments, so we have to go with the transferred learning mechanism. In transferred learning mechanism, what we do is we do not learn from the scratch. We learn in the source domains, import the training experiences, and apply for the target domain. So where we do not learn it, but based on the previous experiences, we apply that learning and do the resource allocation or do the network allocation in the target domain. This is called a transferred learning. Now this helps very much in reducing the computational complexity, because traditional architectures are centralized. In sixth generation, it would be an ubiquitous connectivity in decentralized domain, which needs a lower computational complexity. So transferred learning is a candidate technology from the machine learning point of view or AI point of view in 5G and beyond. Distributed machine learning It reduced the computational complexity substantially by importing the training experiences from the source domain, and it would be merged, and a copy can be recorded at the central domain for a record purpose. That is okay, but centralized version is not suitable because it's highly prone to the failures, and highly prone to the hacking and other things, right? So now blockchain also comes into the picture here. When, let's say, when we share the data, correct, there is, what's the point? How are we defending the security, correct? How are we making sure that everything is secured and shared nicely? So blockchain is very much promising here, along with AI in transfer learning, to make it more secure and make it more decentralized, more intelligent, correct? Because of the parallel processing of AI can be used here, and blockchain can assist to the decentralization part with a secured manner, because it's highly immutable. Blockchains are highly immutable. Along with AI, this transfer learning can play a nice role for this one. So now, one more, what I have observed in some of the papers are like deep queue based joint resource allocation in sixth generation. This is what one example what I have seen. So in this queue learning, what is that? That the agent, the training agent, is continuously interacting with the environment of my network, continuously interacting with the environment of my network. So we can see, based on that, it will continuously observe, it takes the action, it observe what is the outcome, it takes the action, it observe what is the outcome. So it looks at whether it's a reward or is that a penalty, and store them in the array. So now, as I said, the this arrays would be difficult to manage when we have plenty of resource allocation actions, but still it is okay for a medium complex networks. So now they will record those actions, and next time, whenever the next resource allocation request comes, it will look at this array and look at that. Okay, that was the best action which I have allocated, and then we can allocate those similar sort of parameters to the next request. Correct. So, and definitely the deep neural networks can be the part of this one in the queue learning. Correct. So this is another example of a dynamic resource allocation. This tutorial is available on YouTube if someone wants to take a look. So this is very good in YouTube. Correct. So it tries to minimize the channel interference, or by doing the queue learning, it tries to minimize the channel interferences. It takes the care of different heterogeneous traffic and other things, and other channel failures. All these are taken care by queue learning. But the problem is sort of kind of an NP hard problem. So that is one more challenge here. The optimization, it takes too much of efforts to reach the optimization state. So there are other things. So resource allocation, okay. So machine learning based resource allocation. What kind of resources we can allocate? We can apply resource allocation in the channel allocation, apply resource allocation for the power level allocation. Let's say if you're using NOMA or hybrid NOMA or FDM, power allocation is very important. We have to allocate the time slots, which should be nicely allocated in synchronized manner. And there are many other types of resources we can allocate. What we have seen is machine learning with game theory, auction theory, or with the greedy algorithms. My favorite one is the game theory, can do very nice bargain along with the machine learning in the resource allocation problem. So you can propose a hybrid version of a game theory and machine learning. Correct? They are very suitable. Uh, Resource allocation can be a spectrum allocation, also can be a power allocation, also can be a time slot allocation, can be a joint consideration, a hybrid version of this, targeting a rapid response, higher energy efficiency, higher spectrum efficiency, higher throughput, lower delay, higher reliability, higher quality of services. Correct. This kind of outcomes or parameters can be targeted, right? We have to, now for that, the challenge is we have to get the accurate environment modeling, right? What, remember those challenges what we have covered nicely in the first half or first part of the session. So all these challenges such as absorption, human shadowing, higher path losses, rain attenuation, all this whatnot, so you have to be accurately model in that particular environment state, channel state information, and self-adaptivity, because the beams are pretty much pencil. They will not be able to provide the coverage out of that pencil coverage, right? So you have to quickly drift your beam in the direction where the user is moving. So self-adaptability is very important in this, correct? So finally, if I conclude, what we need is new channel model, including all the challenges, new resource allocation schemes, people can work on them, new access technologies, radio multiplexing technologies, what we have to invent. We have to look for energy and spectrum efficiency, correct? Energy and spectrum efficiency. We have to have a new hardware for this. So new hardware technologies have to be implemented. AI integration, definitely. Here you can add the blockchain also. We have to deploy many base stations. So capex and opex. Capex, that means capital expenditure, and opex, that means operational expenditure. See, when we have to deploy too many base stations or too many access points, definitely the capital expenditure would be very high. Also, when we deploy too many base stations or too many access points, operational expenditure would be very high. So we have to deal with the optimization algorithms in such a way before we deploy the network, so that our capital expenditure and operational expenditure comes lower, correct? And so there are specific application oriented improvements also if something is coming up on a demand. Now, okay, so in 1.5 hours we cannot go with entire course on machine learning, but what I have learned from this channel, the Stanford University, they have floated one free course. It's open for all. There is no test that you have to clear to learn. There is no amount has to be paid for this. This is open. So this is not something like supervised machine learning, unsupervised machine learning, not that kind of thing. This is highly maths oriented course, CS 2 to 9, what Stanford has floated. There are around 20 lectures, so they are very good. It covers very thoroughly about the machine learning theory. So this is very good from the research perspective point of view. So if you have students, those who are entering into the research, you can refer this course to them for machine learning. Now deep learning, there are 10 lectures similarly completely on maths. Okay, so you can refer them. I went through that. My students, I referred them to that. They are going through that. This is the channel what they have here. So this is open for all. Stanford learning. So Stanford online. Sorry, Stanford online. These are some of the good speakers, right? So this is Andrew. He delivered all these lectures and they are excellent. Specifically, they are boring. Let me admit that at the first. They are boring, but they are excellent if you are interested in research. Okay, so you can go through and take a look. Okay, so now last question. What's the wow factor, right? So we see theory, where is the code? Correct? We see any paper, there is no code, right? So that's the biggest challenge. Student will come, where is the code? There is no code. So there is no code, right? That's a paper, there is no code. What I want is code, correct? What I want is code, right? From there I'll start. That's where I start. So correct. So there are GitHub libraries. So some of the papers, correct? So it's an open library where you get the paper along with the code, which you can take a look and try at your own, right? So you can change those Python codes or MATLAB codes or Jupyter notebook based codes and apply your own learning there. Change that code, use it for your own research, and use them for further discussions. So that's all I have for a day, and maybe you can open for the questions and answers for a few minutes and let me know. Am I audible?
Yes, sir.
Any questions from the participant side?
Slides were visible, right, madam? Everything?
Yes, sir. Yes, sir.
Okay.
All slides are visible.
Okay. Because initially I found the issue, but later, okay. Let me know
No,
if there
sir,
are questions or anything.
it's very good
Hello,
session.
sir.
And
Hello, sir.
Yes, ma'am.
So, as I have one query regarding that this one device is used for 6G communication. So today we have that lot of mobile handset in our hands. Whether the existing mobiles are suitable for the future 6G generation network?
No, madam, no. Because the radiation is still 5G. See, 4G handsets, even they are not suitable for 5G.
Yes,
Because
yes.
so 6G is a far away. So only key differences you have to take a look. You can open to the mobile settings, correct? There is a Wi-Fi. If you enable, there are two frequencies. You can see 2.5 gigahertz, you can see 5 gigahertz. There are two frequencies only. So they are called current 4G LTE frequencies, 5 gigahertz and 2.5 gigahertz. If it shows you 28 gigahertz, that means that's 5G enabled set, 5G ready set. 5G ready mobile. If it shows you 28 gigahertz also, if it doesn't show 28 gigahertz, that means it's only for 4G. It won't work for 5G even. 6G is far away, correct? So in Wi-Fi settings, you can see if it is sub 6 gigahertz, it's going to work only for 4G. If you pay more and get a new set, if there are 3 frequencies, let's say sub 6G frequencies plus 28 gigahertz, around that, it will work for 5G also. 6G, no one has started the manufacturing because we have to commercialize. So it's not 6G ready. So new sets will come. Just like 2G and 3G mobiles are now, we don't want to use them. So just like that. So it will come after 10 years for 6G.
Thank you, sir.
But 5G ready sets are available. So if you are planning to buy a new set, it's advisable to buy a 5G ready set. Other questions?
Any more queries?
Anything in the chat box or somewhere? I don't have an
The
access
chat
to
box, chat box, I think it's not visible to the participant right now. It's disabled.
Okay.
So participant can ask the queries by unmuting your microphone.
No problem. Sure.
I think so. There is no more query. Thank you so much, sir, for this wonderful session.
Thank you very much, madam, for inviting me. Thank you very much.
Welcome, sir.
If there are any collaborations, if someone is looking for, please divert. We will have the discussions.
Definitely, sir.
Thank you very much, madam.
Thank you.
Thank you so much. Thank you. Now all participants are requested to turn on their cameras for a group photograph. Thank you, everyone. Thank you, sir. Thank you all.
Thank you,
Now
sir.
there will be a valedictory session at 1:30 p.m. sharp. So kindly join, and it's compulsory for all to join the valedictory session. Thank you, everyone.